8:35 a.m. this morning, a man was found dead in central London. The victim was later identified as Rich Jones, CEO of the immensely successful conglomerate Bunny Trademark Incorporated. Starting the papers.
It's all right, John. It's better to look at these cases clear-headed. Now let's see what we can learn from the suspects.
What a place to be found, on the top of multiple buildings.
And get this, each building is exactly 40 meters tall. Intriguing. Is there anything about cause of death?
Nothing that I've seen. Maybe we can look at the crime scene for ourselves. Let's take a gander at it.
Let's see what we've got. There's no way to be sure, but I think the cause of death was blunt force trauma to the head.
But where's the murder weapon?
Aha!
That must be it. Let's go submit this as evidence. Wait, the medical examiner is already arriving.
Determine the velocity with which this rock struck Mr. Jones' head. It might be important to the case.
Well, that's truly an odd request. I've never done anything like it, but I'm sure I could give it a shot.
But wait, how does that have any relevance to the case?
You will see, Watson. You will see.
I tell you with absolute certainty that Mr. Jones was hit with a rock going 28.9 meters per second at an angle of 75.69 degrees south of east.
Incredible!
But Sherlock, I still have no idea how this has anything to do with the case.
Well, what the medical examiner has done for us is provide us with a vector. A vector is a measurement that contains both magnitude and direction. In this case, the magnitude of the vector is 28.9 meters per second, while the direction is 75.69 degrees south of east. Each vector is composed of both a horizontal and a vertical component. All we need to do is determine the horizontal component, and then our case is cracked. Make a list of variables. This is a variable chart. It's going to list everything we know and everything we don't know. For the displacement, which is symbolized as a delta and then an x, we know that we don't know the x, and this is what we are trying to figure out. However, we do know that the vertical displacement was 40 meters, because each of the buildings were 40 meters tall. Next, we have the initial velocity. We do not know the initial velocity of the x, but we do know that the initial velocity of the y is 0, since whenever you throw an object, it at first starts at 0 meters per second downward. Next, let's go to final velocity. Yet again, we don't know the final velocity of the horizontal, but we do know it is the same as the initial velocity, since the air resistance is not great enough to actually make a change. However, we also don't know the vertical. All we have to do to determine the adjacent side length, or the horizontal component, is divide the opposite side length by the tangent of 75.69 degrees.
Sounds easy enough, but how do we find the vertical component? But how do we do that?
We are going to use trigonometry. A vector can be represented as a right triangle, as seen here. The tangent of an angle in a right triangle is equivalent to the side length of the opposite over the side length of the adjacent. Since the opposite side length is equal to the vertical component and the adjacent is equivalent to the horizontal component, all we have to do to determine the adjacent, we don't know the final velocity of the horizontal component. However, we do know it is the same as the initial velocity, due to the fact that the air resistance isn't great enough to actually make a change. We also don't know the final velocity of the vertical component. For the acceleration, we know that the acceleration for the horizontal component is 0, because the air resistance, as I mentioned earlier, is not great enough to actually cause a change in velocity. We know that the vertical acceleration is going to be negative 9.8 meters per second squared, because that is the acceleration due to gravity. Finally, the time. We don't know this, but we do know it is going to be the same between the horizontal and the vertical component.
Yes.
Here's some equations that might help us out. Acceleration is equal to initial velocity minus final velocity over time. Displacement is equal to initial velocity times time plus 1/2 times acceleration times time squared. And final velocity squared is equal to initial velocity squared plus 2 times acceleration times displacement. My old physics teacher always told me that I can forget my family's name, I can forget my friend's name, and I can forget my own name, but I will never forget these 3 equations. Now all we have to do is find an equation that has all the vertical variables that we have, plus the vertical variable we're looking for, final velocity.
Look, that one, that has all of it.
Incredible. Excellent eye, Watson. You sure do have a lot of potential. Would you like to do the honors of writing the equation, substituting the variables, and finally solving for final velocity?
Of course, Sherlock. So, for this equation, we are using final velocity squared is equal to initial velocity squared plus 2
times acceleration times displacement. Since I've already written out the equation on the board here, all we have to do now is to just plug in the variables. So we know that our initial velocity is 0 meters per second squared plus 2 times acceleration, negative 9.8 meters per second squared, times displacement, which is 40 meters. And so, wait, Sherlock, I just realized displacement is negative. You're right. I'm so sorry. It's okay. So now we can get a positive to do the square root. So this all turns out to be 784 meters squared per second squared. So we take the square root of all of that. And so now we get that our velocity, final velocity is 28 meters per second. Perfect. The rock was falling at a rate of 28 meters per second downward. Now all we have to do is plug this into the trigonometry equation. So in order to solve for the vertical component, we have 28 meters per second divided by